Where is it? Yeah. So we are now going to have the next session. This is a session of nonlinear scaling process in the atmosphere and ocean at all scales, from microscales to climate. So I'm François Schmidt. I'm chairing this session together with Isabelle de Lima, and it's a session we organized together also with Sean Lovejoy. So we are going here to have 6 talks. The third one was announced, in fact, was withdrawn, and so we asked Sean Lovejoy, as a poster, to give an oral presentation in order not to have a gap in the program. And I'd like also to remind you that the poster session will be tomorrow. There will be more than 10 posters on display. So we have now the first talk by Mr. Johannes Werner, and so.
Thanks. Thanks first to the organizers for inviting me here to give you sort of the picture that I have, the things that I had to think about when doing the climate reconstructions, which is my, let's say, normal day-to-day job. This is together with Andrea Toretti and Jörg Lutherbacher from Gießen. So first I'll be talking briefly about climate reconstructions, especially about the stochastic modeling, and then the technique that I use to estimate. I think in the where is it there? I think in the program it says testing, but in order to really test something, you have to have good statistics and more knowledge, more data than we actually have. So I prefer thinking of it as an estimate of the stochastic model, and then I'll show you the results, and if time permits, also some of the challenges that we are facing. So climate reconstructions work, to me, all quite similar. You have proxy data, that is climate archives, tree rings, lake sediments, whatever, and instrumental data that represents the target climate field somehow. And you need to have a model to know about the interdependency between those two. Then you use an inference step to estimate the parameters, to invert the model basically, and get a reconstruction. And I'll be talking about the stochastic model only, not about the reconstruction, even though this is my main focus of interest at the moment. So this is a schematic view of a model for okay, then I'll use the mouse of the whole system. So you've got temporal evolution of the temperatures. So you've got, I don't know, interannual temperature realizations that you're interested in. You've got instrumental data that are realization of the temperatures, and proxy data that maybe also depend on the past. This is a picture I stole from Martin Tingley's 2010 article. So those models always need to be as simple as possible, because you actually want to invert them and do things. And but if they are too simple, you're not going to capture the essential dynamics of the system. And I'll be talking about how to estimate this part, the temperature model. In fact, this is a dynamical system that we call weather, and we try to replace this with a stochastic process, with a suitable stochastic process, which we can do because the timescales, the typical timescales in weather are quite a bit faster than those we are interested in. And we can either make assumptions about the system behavior or get the stochastic description from the data, which is what I prefer. I'm using the Kramers-Mial expansion. I did that a couple of years ago with a colleague on a completely different system, and then I'll simplify this. The idea, basically, I guess most of you know, the idea behind stochastic modeling is taking a dynamical system and saying it consists of a deterministic and a stochastic part. So basically this Langevin type of equation and we all hope that it's stationary. And then you can estimate those deterministic and the stochastic part, the drift, and the diffusion part of the stochastic process, or of the dynamical process from the data. So for the drift, what you do is basically you take some x value and you look at how is the mean distance that the system travels from that point within a certain time step tau, and for the drift you take the mean squared displacement, and you do this so basically you shift this red bar over the whole amplitude, over the whole space you have, or the whole temperature space in this case. And of course the problem is you don't have much data here in the more extreme years, in the warm and in the cool years. So those results have to be taken with a certain, let's say, grain of salt and a heavy dose of chili powder. Since I'm a physicist, I prefer the Stratonovich calculus in contrast to Ito, which gives just a correction term here. So we now do this first. Oh, right, and we are actually interested not in the limit, but actually a fixed time step. So we're interested in annual time steps, so we just leave that fixed. And when we do that using, at first, climate simulation, this is a long transient paleoclimate run by Caspar Ammann and co-authors, and we do this for a location, let's say here. What we get out is a drift, so the f of x, depending on the temperature, that looks roughly linear-ish, and you can derive some persistence parameter from this slope, and basically the persistence tells you how does 1 year's temperature influence the next year's, and what you can see is that over the continent it's relatively low, and over the ocean it's relatively high, which we can understand from a climatological point of view. Okay, now to the more complicated thing, the diffusion. If we do that, well, it has a sort of a bend here, though the problem is that we, in order to apply the Kramers-Moyal expansion to this short and let's say quite noisy data, what I did was use a kernel filter to smooth things down a bit, and depending on which filter you use and how the parameters are you use, you can make this even bend down. But this is sort of the best estimate from let's say talking to mathematicians and telling me which filter to use. But well, you could argue that using sort of a constant diffusion does not contradict these results too much. So we can sort of just take that and use that. On to real-world data. This is applying the same thing to only 160 years of real-world data from the crew from the Climate Research Unit, only for summer temperatures over European land masses, since this is my current reconstruction that I'm working on. And we can see we've got a slightly patchy persistence. This is, to my opinion, mostly due to the fact that we have got only 160 years of data. The diffusion, well, the interannual variability of the summer temperatures is a bit higher in the north than in the south, which is known among the climate people. And what I also showed here is the sort of the root mean squared error. So you just average this and then you calculate the root mean squared error. So basically, how bad is this assumption of a constant diffusion of additive noise? And well, for the Mediterranean, it's not that good, but for the rest, one could argue that it's basically okay. So let's say I'm quite convinced that I can that I can use this to estimate the temperature model, and that at least for summer temperatures, the linear model with additive noise seems to be reasonable. I would say it's better than what most climate reconstruction people are using at the moment, at least that. Now on to the challenges, the fun part. We do this for winter too, well, even though climate reconstructions for winter are probably not that easy. Well, basically one of the main climate archives that we use is tree rings, and there's basically no way that you get tree rings that reflects a good winter signal, because trees just don't grow in the winter. You could argue maybe it's snow accumulation or something like that, so you can see it in the spring signal. But not the winter temperatures. So, well, it's a bit more patchy. The persistence is a bit more patchy. Well, there's again this north-south contrast of the interannual variability. But what's now much worse is, let's say, the average error here in the assumption that you use a additive noise. So you need to take this into account. This is problematic because when I do the reconstructions, I'm using Bayesian inference. So I basically have some model like this. You've got temperature depending on the past state plus white noise. This would be the simple model for summer. And if you then convert this to the conditional probabilities for the temperature, ignoring proxies for the moment, just depending on the past and future temperature state, then this looks roughly like this. If you have a different temperature model with a state-dependent interannual variability, so this the updates here, the interannual fluctuations, they depend on the state of the current year. Then you've got multiplicative noise, and now the temperature is going to be in the variance of your conditional posteriors. Well, at least you have to try to get it out of there somehow, which needs an additional Monte Carlo step probably, and all of this will be computationally very, very expensive, and I'd like to avoid that. So the question is, how simple is too simple? So what if we know that the true model is this, so the multiplicative noise, and we use additive noise for the reconstruction? So I created an ensemble of data using this model, then put some noise into that to construct proxies, and then tried climate reconstructions from that. And you can see down here sort of the mean reconstruction error for different noise strengths. So low noise, this is a signal-to-noise ratio of 0.5. Red is signal-to-noise of 1, and green is signal-to-noise ratio of 2. And I use two different error measures. One is the root mean squared error of the reconstruction. This is the closed symbols, and the open symbols is the cross-correlation between the reconstruction and the known truth. And as we can see, as there's the axis label disappeared. So what I did increase was this term here, let's say the non-additiveness of the noise, and as we can see, the cross-correlation drops down quite a bit. What you have to keep in mind is that, in my opinion, the black, the low noise, is most representative for the quality of the proxy archives that we use. So it's still decreasing a bit, but I would say you could probably do that, well, at least until you increase the non-additiveness past a certain point where the cross-correlation drops to 0. This is something I haven't analyzed yet. I'm a bit baffled, but my opinion is that if you look at this model, if you look at the invariant densities, then they probably aren't going to be all that nice. They are going to be, let's say, flat. The system is going to be unbound. And I would argue that this is no longer a climate system. So I used the Kramers-Moyal expansion to estimate the temperatures. The linear model seems to be reasonable, at least for summer temperatures. And, well, what's hardly surprising is that the wrong model reduces the reconstruction skill, but I was surprised at this sharp drop-off down here. With this, I thank you for your attention and eagerly await your questions.
We have time for 1 or 2 questions. Yeah.
Okay. As you increase the multiplicativity of the noise. Yeah. And this is basically, okay, so this is basically what we are seeing there. Okay, great. Thanks.
Okay, so if we have no other questions, so thank you again. So we have now the second talk. So by Peter Huber. So it's also an invited talk. So when it's orange, it means you need to stop.
Okay, thank you for the chance to speak here this afternoon. We're talking about this frequency dependence of climate sensitivity. This is work I've been doing with Christian Prostiesco and Thomas Loppel. In many ways, what this work is an extension of Klaus Hasselmann's 1976 paper on stochastic climate models. And I've quoted that paper here in 2 cases because I think it provides a good introduction to what we're trying to do here. Just to read this, an understanding of the origin of climatic variability in the entire spectral range from extreme ice age changes to seasonal anomalies is a primary goal of climate research. Yet despite the long interest in the ice age problem and the more recent intensification of climate research, there exists today no generally accepted simple explanation for the observed structure of climate variant spectra. And although 36 years have passed, I think this statement still holds true. He goes on to note that a persistent difficulty with these investigations is that the postulated input-response relationship, if it exists, is not sufficiently pronounced to be immediately obvious on inspection of the appropriate time series. This is actually something which has improved a good deal. We have many more paleoclimate reconstructions, both the radiative forcing and the temperature response. And what follows is an attempt to use those records to empirically constrain this relationship, and then to go on and talk about what extensions to Hasselmann's model would be necessary in order to come into agreement with the empirical constraints. So, one more slide of introduction. Here is Hasselmann's very simple model. It's a heat capacity multiplied by the rate of change of temperature, equaling a radiative forcing term that is damped by a negative feedback that's proportional to temperature. Okay. This model can be solved and represented in a spectral domain, here with a frequency axis and a power density spectrum on the y-axis. Then Hasselmann postulates that you have an input forcing, which is energetic at these weather type of frequencies, synoptic timescales, then decays, becomes flat, and then he indicates a bump here, acknowledging that there's paleoclimate forcing mechanisms that may be important. If you use this as input forcing, you can sketch out a response, which is going to be generally red, and then transition to white. Okay, so here is a single slide representing our estimate of the radiation forcing in the spectral domain from timescales of a couple days here out to 500,000 year timescales out on the left. And what we see is much like Hasselmann sketched energetic synoptic variability this is the annual cycle with its harmonics, and then we grade into a white flat spectrum, and again a red spectrum. The various contributions here on the right, this is weather. This has been estimated from NCEP reanalysis over oceans, and what we're looking at here is the median spectra over the oceans of the variance in heat flux. These red curves are compilations of various proxy reconstructions of volcanic activity, solar activity, and greenhouse gas variability, all of which have been summed together to give the blue curve, which is seen here. And that blue curve is fit by a low-order polynomial as a way of representing its general structure. Okay. Now note there is a lot of structure which this polynomial does not represent at the annual cycle as well as at the 100,000 year and orbital bands, and I'll come back to this low frequency structure at the very end of the talk. One can do a similar thing with regard to the response in terms of temperature. Okay? This is a patchwork spectral estimate of marine temperature variability in the tropics. Again, from instrumental and NCEP reanalysis here at the highest frequencies. Then using coral records, magnesium, calcium, and alkanone records in terms of a combination, and all fit with a low-order polynomial. Okay, for reference, the forcing spectral estimates, low-order polynomial fit is given in the dash curve, and one can see their relative amplitudes. As a way of estimating the gain of the climate system, what one can do is take the ratio of temperature response to forcing, and in this case I'm going to use the square root of that value as an indication of how sensitive the climate is to forcing at a particular frequency. That's shown here. I'm retaining a logarithmic frequency axis here, again going from a couple days out to 100,000 year timescales over here, but now we have a linear y-axis, which is in terms of gain in degrees Celsius per watt per meter squared. And what we see is at the very highest frequencies, primarily because of thermal inertia, we have very weak response. And then we grade into a more energetic response, a higher gain, that continues to increase all the way out to these 10,000 year timescales. Okay. For reference, this brownish box here is an indication of typical estimates of climate sensitivity. That is a 2 to 4.5 degrees Celsius response to a doubling of CO2, which would be taken as a constant typically. In some ways you can think of this as an expansion of that estimate into a frequency domain. That response is usually construed as equilibrium if one only considers fast feedbacks. Okay? And what this shows from the paleoclimate data is that if one looks at the entire system, at least during the late Pleistocene, there are clearly additional longer timescales which are present in the system, such that if one wants a complete description, it's also going to be necessary to include low-frequency feedback terms. Okay, I don't think that comes as a surprise in many ways. We know that there was ice ages. We know that there's been these long-term shifts in the climate system, which in some ways have reinforced temperature changes. Other issues being things like changes in land cover, changes in sea level and exposure of continental shelves. But what this does offer, and I think for the first time, is an empirical constraint on what that gain function actually looks like. This is in many ways a qualitative representation because there's many other issues associated with the proxies that one would want to think about carefully. I'm just trying to give you a broad brush. In other work, some of which is submitted with Thomas Loppel, and in preparation with Christy Prostiesco, we deal with many of these issues in detail. What I would like to point out is that if one even looks at a lower bound or an upper bound sort of estimate in terms of what this gain response looks like, we can think of this as roughly an 80% confidence interval. We always have this structure whereby gain is increasing markedly all the way out to very low frequencies. Okay, so then the question arises of what sort of simple model would fit this sort of structure. And we can take as a starting point Hasselmann's stochastic model. And a solution in terms of gain space is given here, 1 over a term that's proportional to heat capacity and frequency plus this negative feedback term, which defines where you're going to have a rollover from a red to a white. And it's a fairly rapid rise in gain that then levels off. And I've chosen a value of lambda such that it's in general agreement with the climate sensitivity estimates for fast feedbacks. Okay. In no way am I able to tune this model so as to fit the specific gain estimates that one's getting from the proxy record, because this rises too quickly and then it levels off too flatly. Okay. But what we can do is augment Hasselmann's model. One thing to do would be to include ocean diffusivity, as others have also done. Specifically, what we have here is linear coupling at the base of the thermocline with a diffusive interior of the ocean, where you have vertical diffusion of heat downward. This introduces an additional term into the gain function here, which is going to be proportional to kappa times the square root of the frequency. And generally what it gives is a large range of relaxation times that are going to be slower than what one would have with just this mixed layer representation that Hasselmann presented. And you get this blue curve. Okay. In no ways does it fit the low frequencies any better, but you can see at the higher frequencies here, where in this case higher frequencies is centennial and shorter time scales, you can actually get a better fit to the observations. Okay. Now, the final step, we can look at the frequency-dependent climate sensitivity when we introduce a low-frequency feedback. Conceptually, what this is an ice sheet that has implications for temperature because of its albedo. It's indicated here by lambda TV times the degree of ice volume. Again, we have this coupling to a diffusive interior ocean, and we have changes in ice volume, whereby ice volume will increase as temperature decreases, but the extent of the ice sheet will be limited by the fact that there is limited area at high latitudes on continents. Okay. Once again, it's possible to solve for the gain function associated with this set of equations, and we get a new term. Okay. And what this term represents is the interaction between albedo and growth of ice, and it's scaled by frequency and a roll-off frequency here that's associated with the time scale of ice sheet variations, which is taken here as 1,000 years. Okay. Similar to what Weertman postulated at the same time as Hasselmann's paper back in 1976. Okay, now we get this red curve, okay, and it's clearly overfit given the uncertainty in the observations, right? But what the point is, you can get a general structure which is similar to the gain response which is observed, okay? And the most important point of which is not that the pointer is dead, but that the most important point of which is that you can get these very low frequency increases in gain, and they're ongoing. That's it. Yeah, thank you. Okay, great. I think the battery's just probably going low. Okay, and so I think this is a useful first-order description if we want to talk about the gain response going all the way from synoptic to glacial, interglacial cycle timescales, whereby both diffusive coupling with the deep ocean and this very slow feedback thought of conceptually here as an ice sheet are sufficient to represent the overall structure that we're empirically observing. Now, I've run a little bit roughshod over the low-frequency structure that we know is in the forcing and the response spectra, and I'd like to return to that in a single slide here. In this case, I'm using the Vostok and the Epica Dome C records. Delta O18 is an indication of temperature, and greenhouse gas reconstructions is an indication of radiative forcing. Because they come from the same core, the same set of cores, we have less issues associated with timescale uncertainty, and that makes it easier to make a comparison. But this is that radiative forcing from the greenhouse gases from the Vostok and Epica Dome C core. And here we have a temperature response estimated from the stable isotopes. This is using the EDC 3 timescale. And what we see is this is a logarithmic axis on the y-axis, and so we have much of the variance concentrated at the 100,000 year periods here. Fully half of the variability in both the temperature and the radiative forcing is here at this 100,000 year glacial interglacial timescale. We also have peaks at obliquity and precession. Now we can take the ratio of these two again. It gives us a gain using the square root of that ratio here. Whereas before the gain was about 1.5, where we're looking at tropical temperature records. Now we have these high latitude records, and we have a much more intense gain of about 5 degrees Celsius per watt per meter squared as a baseline. Okay, we have this incredibly strong gain here at the obliquity band, but that's because we haven't represented the radiative forcing fully We know that there's a CO2 response to changes in obliquity, but there's also a direct radiative forcing of Antarctic temperature by obliquity, and that gives these very high values. What I find particularly interesting, however, is that if one looks at the average gain at the high frequencies, it's the same as the average gain at the 100,000-year timescales. And what that says is that the suite of physical properties which governs the response at these high frequencies is probably also sufficient for explaining the 100,000-year variability in temperature in Antarctica. Another way of putting that is if we understood what changed atmospheric CO2 at 100,000-year timescales, it seems like it would be straightforward to understand what changes the temperature at those same timescales. So by way of conclusion, first off, paleoclimate and instrumental data permit for estimating the spectrum of radiative forcing and temperature response. The associated gain estimate demonstrates that temperature sensitivity continues to increase out to 10,000-year timescales. This empirical gain curve is consistent with Hasselmann's model after including terms for diffusivity of heat and variation of ice volume. And finally, the gain at the 1 over 100,000 kiloyear frequency is consistent with that at higher frequencies, indicating a common set of mechanisms that serves to explain the 100 kiloyear variability in CO2, and will also represent a complete explanation for that variability in temperature. Okay. If I have time for questions, I'd be happy to have them.
Thank you. So we have time for one question.
Two things that are related. One is this: essentially assume you know what forcings are, and then you assume there's a linear relation, and that extends over this huge range. So isn't that one of the whole problems? Is what are the forcings? The possibility that there could be highly nonlinear gains, different types of forcing, etc. I mean, anyway.
Yeah. Perhaps there's an objection to speaking in completely linear terms in a nonlinear geoscience meeting, but the I think there's a couple answers to that. One, we do have a good sense of what the direct radiative forcing has been. The one thing that hasn't been included here is changes in aerosols. You can consider that to be a feedback. A more complete cataloging of what that radiative forcing looks like, I think, would be helpful, but I don't think it would change the general answer here, that what we're seeing is greater gain at lower frequencies. The assumption that this is a linear response, I think, is the appropriate first-order starting point. Let me see how far we can push that. In so much as the 100,000-year timescale response seems to be explainable as a linear response consistent with what we're seeing at the higher frequencies, I think is interesting and maybe would suggest that it's actually a relatively simple explanation that's possible.
Okay, thank you. Thank you. So we had a withdrawn talk in the program, so we asked Sean Lovejoy to give his poster presentation as a short oral. So we have now Sean Lovejoy.
Okay. So, good afternoon, and this should be considered more light entertainment to fill the gap that would have been here if the speaker had come. Whoops. So what I'm going to try and explain why I have this perhaps strange-sounding title. The real title, or the real content, is actually how fluctuation analysis can transform our view of the climate. And I just mentioned that there's a book that's coming out any week now, which has a lot of this stuff in it, and other things as well. So why this strange expression? Well, it's kind of a popular expression for defining the climate. It's, of course, not. It's this thing here. It comes from the climate is what you expect, the weather is what you get. And actually, this citation here, it seems to be the first place where this was exactly said this way. Many people claim it was Mark Twain, but anyway, it's obviously something that is in popular culture, and it just gives you the idea that the climate is a kind of a long-term average. And this is actually quite similar to Other definitions, here we have the U.S. Academy of Science. It says climate is conventionally defined as the long-term statistics of the weather, and they add the fact that you could include oceanic and terrestrial spheres and chemical components as well as just the weather. But people like Ed Lorenz even had a paper with this title, "Climate is What You Expect." So clearly this is something that, was considered not only a reasonable definition of climate, but even something that should be hoped for. We should strive for models, say, that have this property. So I'm going to try and tell you why this is not, in fact, correct. The basic reason is that, in fact, we have a kind of a trichotomy, not a dichotomy. When you actually look at real data, you find that, there's two data sets here. One is essentially instrumental data from reanalyses, and then I have data from a single core paleo data in the Arctic. And you can see that up to about 10 days, you've got, this is for the temperature, but it's roughly, the spectrum increases roughly with the power law. Then you get a different power law that's got a very shallow slope that goes to about 30 years, and then it increases with yet a different power law roughly to about the period of the interglacials. Okay. Now, in those three regions, the character of the fluctuations of the temperature look totally different. So, for example, we look at the bottom weather regime. This is data at 1 hour resolution, and it essentially looks like you have a drunkard's walk, right? So you get an exponent, h.4. I'll define that more precisely in a moment, but that just tells you how rapidly the drunkard, on average, moves from, a starting point. So how rapidly do 2 points on this curve diverge in the vertical, in fact, as time goes on. So it's, in fact, not far from Brownian motion, which would have 0.5. Okay. So, however, when you go to 20-day averages, so now we have 30 years here. Each of these has 720 points, by the way, so there's a fair comparison. So we now have 20-day averages. I actually did this at the Greenland location where I took the spectra before, but you see a totally different character. You see, if you get a fluctuation going up for one period of 20 days, then it's usually followed by compensating, and then that's compensated, et cetera. So you can imagine that then, looking at this curve here, if we use the aphorism, the climate is what you'd expect, and you said let's just average longer and longer scales here, that you would get effectively convergence to smaller and smaller values as you average this over longer and longer scales. Okay, and indeed, there's an exponent here that tells you exactly how quickly that converges to zero. And you'd expect, if the climate was what you expect, that this would just keep going for longer and longer scales, and all you'd have to do is average more and more, and you'd get a good estimate of the climate. But when you go to 100 years, instead of finding something that's actually smoother and smoother, you find something that, on the contrary, looks like the weather. So the climate, these 100-year average curve here from Vostok, has almost, in fact, exactly the same exponent as the weather. So it's actually just as unpredictable as the weather is. So you've got this intermediate regime that I'm calling macro weather, and that's actually what you expect. It's not the climate, it's macro weather. So just a quick point that you have the same behavior in the ocean for roughly the same reasons. Because it's turbulent. So you see here, this is the atmosphere temperature, and then I kludged together this with another over land spectrum up to about 100 years. Then you can see things are starting to go up again a bit. But, okay, so that's the picture, and you can see this transition period is roughly the lifetime of a planetary structure in the atmosphere, about 10 days. And this works out all very well if you take the turbulent energy flux that you can deduce from solar forcing, in fact, distributing this over the troposphere, making assumption about efficiency of conversion to kinetic energy, and putting in, using the observed scaling of the velocity, in fact it's a Kolmogorov scaling, you get about 10 days. If you do the same thing for the ocean, you see here you have a turbulent spectrum again for the current, and you take the observed value of this energy flux. This is actually these units are the equivalent to watts per kilogram. So you have about 10 to the 5 times weaker turbulent fluxes near the surface of the ocean, and you get a time scale which is, in fact, the ratio 10 to the 5 to the 1/3 power. It's about 1 year, in fact, at the end of the day. And so theoretically, you get a very good explanation for these breakpoints, and you get, again, a drastic change in the spectral behavior here, but it's not identical, but it, in fact, has the same qualitative behavior, as I'll show momentarily. The point is that if we look at things in spectral space, it's all very well, but the interpretation is not so clear. So it was not obvious, for example, that when that the character of this regime and this regime were more or less the same, whereas this one is totally different. And the reason is that the transition slope is about 1. So the key critical slope for getting fluctuations that grow or decrease is roughly 1. And to see that, you can look at fluctuations in real space. I'm just looking at the mean fluctuations, so you could look at multifractality, which we have done, of course. But the main thing here is to look at the mean fluctuations, and you can see that they increase when this exponent h is positive, decrease when it's negative. And, okay, these are the regimes that I just discussed. Okay, you could say, let's do this properly, but we don't actually need sophisticated math for this, which is one of the interesting, there is a sophisticated reason why everything works out well, of course, but if we just want to understand the fluctuations, it's enough to do it in simple words. Of course, there are infinite number of ways of defining a fluctuation. The traditional one is just as a difference, the difference in temperature between T and T plus delta T, for instance. This one is not really used, but you could imagine very easily that the tendency is just the average after you remove the overall mean of the series, then you average it between T and delta T, and you can see how quickly the averaging makes that go to 0. That would be if H was less than 0, here if H is greater than 0. So you can put the two together in something called the Haar fluctuation, which just takes the difference between the average of the first half of your interval and the second half of the interval. That actually corresponds to a Haar wavelet, in fact going back to 1910, but you don't have to know anything about wavelets. The key point is that there's a combination of differencing and averaging, and that allows us to use this definition of fluctuation for any h exponent between, in fact, +1 and -1. And when when you're in a region where h is positive, it's the differencing that dominates this, and when h is negative, it's the averaging that dominates. So how does that work? Here's some instrumental data. So you're going to have to get used to the fact that one of the big advantages of this technique is you can compare all kinds of things very, very easily as a function of scale. Here I'm looking at actually the RMS fluctuation, but you can look at any moments you like and look at the multifractality, in fact, that way. But anyway, here I've got some hourly data, so you can see the weather regime. And then at around 10 days or so, it starts to decrease. Fluctuations decrease, so you get plus or minus, this is 10K, your amplitude of your fluctuation, so you can read off the value exactly in degrees Kelvin. If you do spatial averaging, so instead of looking at a single thermometer here at a station, you look at a 2 by 2 degree grid, and actually this is at 75 north, this is averaged over the Earth, but you get, the magnitudes are a little different, but the slopes are almost exactly the same. You could look at the average, the temperature globally, and then do it again. Once again, the temperatures rise up to about 10 days. Fluctuations rise, and then they decrease, but maybe more slowly. You could look at global surface series, which also do that. And the interesting thing is then that something around 25 years, and actually this is highly variable, and we'll get to go into a long discussion about this, but somewhere around there, things turn around. So this macro weather where fluctuations where you really have this climate is what you expect idea, where you average longer and longer, that you do indeed get these fluctuations dying down, 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 but then it turns around. And it must turn around because otherwise there would be no ice ages. I've just inputted here some multi-proxies, which I'll come back to, so this is not real data, but okay, we could look now at paleo data this way, compare a few. We've got 2 Greenland cores, Vostok, Epica, Grip. The point is that somewhere around 50,000 years, and you should get fluctuations of the order of ±3, ±2K. That's what I call the interglacial window. we're expecting the curves to go through there, and they almost do. So the point is, though, that they have to go down and then up again. Somehow they have to get up here. So the going down, 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 the macro weather has to end, and whether it does so in a power law the way the data indicates roughly or not is maybe secondary importance. The key is it has to go up again. You can even go really far, and this is actually some data I stole from a paper by Peter, who just talked, the pink curve. This is not really interpretable exactly in terms of temperature, I should say, anymore. This is from the ocean core benthic isotope ratios, and they've been converted using a rough conversion into temperatures. And there's a couple of other assemblages here that take us out to actually several 100 million years. And you can put the whole lot together, and you can see, okay, it gets very messy. Oh, whoops. But you get the overall picture. Temperature goes up, goes down. It has to go up again to the ice ages, and then, okay, back goes down. But, okay, over here, several million years, not so clear, but okay. So I have another 2 minutes. So this already gives you the idea of the kind of thing you can do with this. If you want, you can evaluate multi-proxies. I looked at many of them. It turns out that the multi-proxies, I looked at 5 before, early ones, 2003, and they do indeed decrease to 25 years or so. Then they increase to about a century, but then their multi-centennial variability is low. They go down. If you look at some of the more recent ones, there's 3 of them here. On the contrary, they keep going up, and it looks like they could be extrapolated to what it has to be for the ice ages. They have to go through there. Okay, you could assess solar forcings. Here's some real data. The interesting thing is that, so you have solar reconstructions based on sunspots. You have another one based on sunspots, but roughly increasing. Another one based on sunspots, roughly increasing. And then you have the interesting thing based on beryllium-10 going way, way down. But they agree at 100 years in terms of the amplitude, so nobody noticed the fact that their behavior is completely, completely different. And this one's a more recent one, but also beryllium-10 and also decreasing. So you can then see, if you want to look at the question of the response, here's the temperatures. You can put the two together if you assume climate sensitivity of about 4.5 K per watt per square meter, which corresponds to about a factor of 15, in fact, amplification, nonlinear amplification. And you can see that all of these effects, the only one that might work if you had such an amplification was if the sunspot-based solar continued all the way. You could look at volcanic. The volcanic, on the contrary, goes down very, very quickly, as you expect, because there's a huge effect at the short scale, and then it gets averaged out. And so it just seems unlikely that the volcanic forcing could explain a signal which is increasing. And here you could put CO2, etc. Okay, well, you could also I'll just end on this last thing. You can look at GCMs here. The GCMs on the control run go down, down, down. They do macro weather out to several thousand. Well, they just probably go forever, decreasing. So climate is what you expect, but then you put climate forcings, and the models improve a little bit, but they're still below where they should be, and it looks like they're still the wrong way. Instead of going up, they're going down. So, okay, I better stop there instead of... Oh, this was just a GISS, the last one, hot off the press, a GISS-E model with various volcanic scenarios, solar. You can see the volcanic scenarios are overestimating the true thing, which is the surface, this blue thing. They overestimate the variability, and then when you get to several hundred years, they underestimate a bit. And this is then multi-proxies here. So, whereas the solar is just too weak and increases a bit, but okay. So you can use this to evaluate all kinds of stuff, and we could talk later if we want.
Time for a short question.
All right. Well, I can't possibly answer all those questions in a moment, but as far as the volcanoes go, I didn't rule out. I mean, all I'm saying is that their radiative forcing rapidly decreases with time scale, whereas the temperature increases rapidly with time scale. So, but that doesn't prove that an appropriate amplification mechanism, the amplification mechanism would have to increase almost linearly with time scale. It may exist, but that must be demonstrated, and it's certainly not at all obvious that it does exist. So anyway, maybe I should answer the other questions in private afterwards. Yeah.
Okay. Well, thank you. So we now have another invited talk by Toby Holt. So when it's yellow,
All right, thank you, and thanks for the invitation to talk. It's really exciting and an honor to be here with some of the people whose ideas I have used in trying to come up with a real application for this idea of scaling and the kind of inferences we can make about prolonged drought risk or megadrought risk in the future. Start with a definition for megadrought because it's been used to describe prolonged periods of aridity on a wide range of timescales, ranging from a few months in the case of the Amazon drought of 2010 and also from thousands of years. So from Wikipedia, which is convenient because probably someone who's here wrote this definition, or maybe someone who's in the room. And the thing I like about it and the thing that I think really captures what a lot of us mean when we talk about megadrought is this prolonged aspect of a decade or a few decades or longer, and also the human consequences, the consequences for civilization, for society. And of course, it goes on to say that, as such, these events constitute one of the greatest risks or greatest threats to civilization. So we should really understand how likely they are in the future. And because this is a session on processes across a wide continuum of timescales, I thought I'd try to put megadroughts in this context. So the black to gray shading just shows basically the precision of the apparatuses we have for understanding climate fluctuations in these timescales. So for weather, we have satellite data, we have other types of data as well, with coverage of a few decades, and it gives us a lot of information at pretty high resolutions in time. Instrumental records, of course, maybe lack the sort of highest frequencies in that context, but they have more temporal coverage going back at least a few decades, not a few centuries in Europe and other parts of the world. And then we have paleoclimate archives, which typically, at best are resolved down to a month, but usually more like a year at the highest frequency or a decade or a few decades. And then we have global climate models, which we can use to try to understand how the whole system fits together in an atmospheric ocean-coupled system. But again, the precision in the sense that you're not looking at data anymore when you're looking at GCM output. You're looking at the response of a model to the prescribed boundary conditions. So we've got this problem because these very consequential events, megadroughts, are occurring right at the edge of our ability to observe the system. I think in the 20th century, it's safe to say that we only had really one megadrought, the Sahel megadrought, which lasted several decades during the last part of the 20th century. And so we have to use paleoclimate data and we have to use GCMs to try to get at the statistics that govern the underlying system on which these things occur. And so we have to put these data together somehow, and as Sean just pointed out, the power spectrum in doing these things in frequency space is very convenient because one would expect that things like internal sources of variability, natural variability, might evolve differently in a global climate model simulation than they would in reality, even if they're fundamentally the same. So if the amplitude of some oscillation in the North Atlantic or in the Pacific Ocean is comparable in the model and in the reconstructions, but happening at different times during the simulation, we want to be able to see that. We want to be able to capture that similarity, and doing it in frequency space works reasonably well for that kind of a comparison. And again, and the spectra that I'm going to show pretty much all have this time coverage from about 2 years on the right-hand side of the x-axis to 1,000 years on the left-hand side. And megadroughts, they're occurring on these multi-decadal timescales, so right in the middle of that continuum. Now, with the question of drought or with hydroclimate variability, there's a couple additional considerations that I think are worth taking into account before just looking at power spectra. So on the left column here, we just have time series from Montana. On the top is precipitation. In gray is the monthly precipitation for Montana, for the whole average over Montana. And then the black line is the annual average, so of course the decrease in variance. And in the right-hand column are the spectra, using MTM to calculate the spectra. And what you can see is for precipitation, the power spectrum is pretty flat in these longer time scales, and there's no real offset between the precipitation and the monthly or the annual time scale, which makes sense because it's a pretty flat spectrum. When you move to the z-index, which is basically a moisture balance metric, precipitation minus evaporation, doesn't take into account any effects necessarily of the surface. It's basically just a temperature term and the precipitation term isolated. Looks a whole lot like precipitation, and in frequency space that's also true. Then when we move to the Palmer Drought Severity Index, or PDSI, there's a term that's built into this Palmer Drought Severity Index which carries information from one time step to the next, from 1 month to the next. And that's supposed to represent the persistence that is inherent to soil moisture. In most of western U.S., this term from 1 month to the next month, the autocorrelation parameter for most of western U.S. is about 0.9. They use 0.87 in the PDSI calculation. And then on the bottom is soil moisture, which is simulated numerically using the VIC model, variable infiltration capacity model. And on the bottom right, the two spectra from both PDSI and from soil moisture are much redder than the overlying sort of atmospheric spectra from precipitation and from temperature. And so because we know in PDSI what that autocorrelation parameter is, we can model the spectrum analytically, which is what's shown in that black line. So we can do that from the monthly time scale up, and I'm only showing the interannual portion of the spectrum from 2 years to 1,000 years. And of course, it flattens out as expected at about 10-year time scales. And then we can do Monte Carlo simulations and get very similar shape to the spectrum. And the important part really is just that it flattens out at the decadal and longer time scales. And so when we compare that with paleoclimate records, we see something kind of interesting. So we've got our expectation that there should be a little bit of redness in the spectrum from 2 to 10-year time scales. And we see that in the Monte Carlo estimates. We see that in the analytical expectation. When we look at reconstruction, so the purple and the red lines are average spectra from all of the stream flow and precipitation reconstructions that are available on the NOAA Paleoclimatology website for Western North America. They're more energetic on interannual timescales, and they're well within the range of the null hypothesis on the longer timescales. Now, we also looked at the mean power spectrum from a database that Connie Woodhouse and others put together of 5-needle pine chronologies. And this is important because these are really long chronologies that have really long segments and have the best chance of capturing and retaining low-frequency information beyond what shorter segments and shorter time series might be able to do. And when we look at those, that's the gold line, they seem to be rising above the expectation on at least century and longer timescales. And then the same is true for the other types of paleoclimate, paleodrought, or paleohydrology indicators that we examined for this plot. So on the longer timescales, it looks like this, we're definitely seeing some evidence of low-frequency variability beyond what we would expect from just local sources of persistence or from autocorrelation. So there's a role, it's interesting. There's a role for climate there. And just to go into the tree ring data, because there's a number of questions that when we first started doing this, collaborators who are dendrochronologists were raising questions about whether or not this was really an accurate portrayal of the climate system in the West, because what it would imply is that you really only need weather and interannual variability to get the spectrum of most tree ring reconstructions of hydroclimate. So we dove down a little bit deeper into the longest moisture-sensitive actual ring widths, so not just the chronologies, but the ring width measurements and indices that you can get from those ring width indices. And we looked at the longest ones and looked at different detrending techniques. What we basically found was that there is evidence for low-frequency redness on timescales beyond a decade or so. So when we look at the expectation here and the agreement between the tree ring reconstructions of various hydroclimate indicators, that's somewhat misleading. It probably reflects pre-processing choices and other methodological considerations that went into the reconstructions, but doesn't necessarily tell us much about the longer timescales. So then we can move on to the global climate models. These are the from CMIP5 archive. There are 7, at least last time I checked. There were 7 last millennium simulations. So they're forced with dynamical boundary conditions, orbital, solar, land use change, grazing greenhouse gases during the 20th century. And the upper left is the controls for each of those same 7 models, and volcanic variability as well. So what you can see is that, consistent with what we would expect for Western North American hydroclimate, the controls are kind of within that range, but so are the last millennium simulations overall, which is a little bit surprising because they mostly have trends during the during the 20th century. There's one model when you look only at the 850 through 1850, so basically the pre-industrial forced simulations, the portion of those simulations before the real anthropogenic influence kicks in. Most of them, again, are in agreement with the null hypothesis. And then when you look only at the 20th century portion, it's not really long enough to say very much, but it agrees well. You can see that there's some interannual peaks, and those correspond to very energetic interannual ENSO fluctuations emanating from the tropical Pacific. The dashed line is that multi-proxy spectrum. So there seems to be a real disagreement here between what's being simulated of the last millennium and what we think we've recorded in terms of hydrology or hydroclimate of the last millennium. And so the first pass to try to estimate drought risk or prolonged drought risk was to just look at these different realizations, Monte Carlo realizations of the Palmer Drought Severity Index, or PDSI. In the top part, we just use like a white noise driven, like your run-of-the-mill autocorrelation model. We just hit it with white noise proportional to what's expected for the West. And what's being shown here is the PDF of 1,000 realizations of this AR1 model. And on the y-axis is the duration of the droughts, and on the x-axis is the magnitude. And what you can see down here on the x-axis in the top panel on the white noise-driven model, I'm really not seeing any prolonged droughts of more than a half a unit, which is basically a standard deviation on 50 and 40-year timescales. Whereas when we use a power law to drive to try to model PDSI, it looks pretty similar on the shorter timescales, but on the longer timescales, you can see there's much greater risk, or there's a much greater apparent risk, 10, 15, 20% of these prolonged events in the longer timescales. But that's not really a complete picture of the future because that's assuming some sort of stationarity, and we know that the mean is not expected to be stationary for the next coming decades or centuries because of climate change. So we turn now again to the GCM world and try to get some more constraints or some more information to make these kinds of assessments. And this is just to back up a little tiny bit for some background on what we're doing now. This is a paper we have over the summer. And we were just trying to look at the relative strength of decadal components in observations versus models. And what we found was that when you look at, this happens to be the GPCC precipitation data set, but we looked at others as well. What we found is that in general, over most continental regions, the relative strength in terms of the percentage of the total variance of precipitation, decadal components and decadal and multi-decadal components in observations are much stronger than they are on average and even model to model. And you can see that there with decadal components comprising something like 30% of the spectrum, which is actually consistent with the power law distribution, and more like 10% or 15 or 12% in most of the models. So there's some other caveats that are just worth mentioning, and if you can't accept that the things that are in the black column there are appropriate, then our risk analysis is not going to be useful, it's not going to be meaningful. But there's a bias towards being too wet. Models are typically too wet on the order of 15 to 20% on average when you average out precipitation throughout the world. We still can hope, we can assume that the relative changes of a 30% or a 10% reduction is predicted, that's at least physically plausible. They have systematic biases. I mentioned already that they have too much interannual variability with respect to decadal variability. There's also well-known biases in the tropical Pacific, both in terms of the spatial extent and structure of ENSO, but also in teleconnections and in the amount of variance on interannual timescales in the tropical Pacific. And then the other part that I'm actually going to try to deal with a little bit in the next few slides is that there are we do these averages of multi-model ensembles, but they're not really truly independent because they share code very often. So a great example is the NCAR model. Its atmosphere is basically the same as the Norwegian model's atmosphere. So we're making averages of things that aren't necessarily as independent as we think we are. And so we try to identify, and this is actually work that Reto Knuti and Ben Sanderson and others have worked on, to try to identify clusters of models that have some shared view of climate. And so we apply this rescaling technique to try to get some of the low-frequency variability that we think is missing from the models back into them, just in a statistical sense to address risk. So here's like a raw power spectrum from GCM. This happens to be a control run. And it's pretty flat, white noise distribution in frequency space. For the same grid point, this is the southwest, we expect a power law of about 0.4, 0.5. That's kind of the low end of the estimates that we got from the paleoclimate record. And so we just filter it in frequency space. So we filter the Fourier transform and then we repeat the Fourier transform, the inverse Fourier transform, the filtered Fourier transform, to get back a time series whose spectrum now has this distribution that we think is more appropriate for the region. So we do this, and we define a megadrought as a 10-year period of aridity on the 25-year mean, which is consistent with one of the biggest megadroughts that happened in the Colorado River. And when we test it on the control simulation, we get no megadroughts when we look for them in the control simulation of CCSM3, and we get exactly one over a millennium-long simulation, which gives us some hope that we're on track here. And we look at the projections of the future. This is the same model. So the blue line is the raw precipitation at annual timescales, and the yellow line is the rescaled precipitation on the top. It looks pretty similar, so the rescaling doesn't seem to have much of an effect on the interannual timescales, but in the longer timescales you really see it, and you get one megadrought in the future. And we look at the Southwest, and we look at the percentage of models that experience such a drought, and you can see that there's a slight increase, and there's an increase in the timing in the Southwest. And then we look at these clusters, and I'm running out of time, so I will just go straight into the clusters. I'll get the whole thing up here. So basically what we're showing is that for all models, the ensemble average looks something like, let's say, 10 to 15, 30%. When you look in these individual clusters, risk increases substantially. And then when you rescale, especially when you rescale the most extreme scenario, RCP 8.5, you see a big difference. And I will go all the way to the end here, because I think the most important part of all of this is that the rescaling applies most and most critically to pretty stable situations, so either the control runs or the very moderate warming scenarios. And once you get into the really strong, severe warming scenarios, the risk of a megadrought is pretty high whether or not you rescale. And there's some future work that I'll let you read about. So, thank you.
So only one short question, please. Yeah.
I suspect that it's a combination of too much interannual variability. So the interannual components in the models are just kicking so hard that they're really imparting a lot of variance in these shorter timescales. That was certainly the case in CMIP3. I suspect it's the same in CMIP5. The other part could be, and this is just an opinion that I haven't really looked into too carefully, but if there's a fundamental like temperature fluctuation that is power law scaled on the longer timescales, and that especially once you move out past the ENSO frequencies, is propagating into the hydroclimate hydrological system, that could be a real source of mismatch. When you look at the patterns globally of some of these things, it seems to be consistent. So as a hypothesis at this stage, it seems to be consistent anyway, that it's a temperature fluctuation, amplitude of temperature fluctuations on decadal and multi-timescales that just aren't as energetic in reality, partly because of the interannual components being too strong, too loud.
So we have now the next invited talk by João Teixeira.
Good afternoon. Thank you very much for the invitation. I will very briefly try to summarize what the turbulence problem is in the context of climate prediction. And it will be a brief and simple summary. And So you all know that basically climate models or weather models are based on the momentum conservation equations, energy conservation equations, mass conservation equations. We can't find analytic solutions for them. We cannot even prove that there are analytic solutions. And so what we have to do is discretize these equations, right? We break them in little boxes or big boxes and solve algebraic equations for each box. And for climate models, in particular, because of computational resources or the limits of computational resources present day, we have to break it in boxes of about 100 by 100 kilometers, this sort of order of magnitude. And you just need to look outside, right, and realize that clouds are not boxes of 100 by 100 kilometers. They have structure, they have small scales, there's a variety of complexity there. On the other hand, yes, you can just... On the other hand, the small scales do matter. So if the small scales were irrelevant, then we wouldn't have to worry so much about what happens. But it does, in fact, matter what the small scales do, and the large scales are impacted because of that. Now, what I have next to the climate model is a little plot from a high-resolution model that I'll just talk about in the next slide. And you can see all these different convective structures. And one simple thing you can do is actually to look at the most simple statistical properties of these structures. So you plot a PDF of the temperature and the water vapor, the thermodynamic variables. And this is what we do in this plot. So this is water vapor here. I apologize for the quality. This is temperature, and this is the histogram or the PDF plotted from this actually realization of the flow. On top of that, you can actually plot sort of a stability line, what we call the Clausius-Clapeyron, which tells you that all the points above that white line are inside a cloud. So that's the cloudy part, and all the points below the line are clear sky. And then fundamental things like calculating how much water, how much liquid water exists in the box, and how much cloud is the box covered with, so the cloud fraction. So something between 0 and 1, which is the fraction of the box that is covered by clouds, can easily be estimated as long as you know what the properties of that PDF are. So it turns out that in many respects, the key problem is finding what are the dynamic equations that regulate the statistical properties of the flow. And in particular, this covariance over here, the covariance between the vertical velocity and any scalar or dynamic variable, is the fundamental quantity in terms of turbulence and convection. So you obtain that equation very simply by doing some Reynolds averaging and decomposition. You end up with an Eulerian tendency for the mean in the grid box, plus the sort of resolved advection term, and then you have in atmospheric models a vertical divergence of this covariance. So the zero order problem in terms of climate prediction and weather prediction is really calculating what the properties and what the equations are for that particular covariance term. So turbulence and climate are really intimately connected, and my point here in this slide is really to highlight the fact that I think is not sufficiently mentioned, that the climate prediction problem, at least the climate prediction problem in the scales of 10 to about 100 years, is essentially a turbulence and convection problem. So understanding turbulence and modeling turbulence is an essential step towards better climate prediction. And it is true for cloud climate feedbacks, which is about, in the end, cloud climate feedbacks are about the interaction between a very highly turbulent flow that changes phase and interacts with radiation in funny ways. Or the problem of predicting how extreme weather is going to behave in the future is about how moist convection responds to a warmer world. And the same thing for ocean. I mean, ocean mixing plays the key role in determining how much CO2 and how much heat is going to be absorbed by the deep ocean. So it's intimately connected to climate. Now, what are the tools? And in this next few slides, I'll essentially talk about the tools that we use and highlight a couple of them. And our one of the key tools that we have to understand and come up with those dynamic equations for the statistical properties of turbulence is to use what we call large eddy simulation models. And large eddy simulation models, again, are models that are in many respects similar to climate models. They're based on the conservation of momentum, the conservation of mass, the conservation of energy, except that they are actually solved in domains that are around 100 by 100 kilometers, which is exactly the size of a grid box in a climate model. So the climate model has a domain that is the entire globe. The LES has a domain that is the size of a grid box of the GCM. But the resolution of the LES, so the large eddy simulation model, is really boxes of, let's say, 10 by 10 by 10 meters. So there's two great things about it. One is that most of the important convection and turbulence vertical mixing that happens in the boundary layer and in the atmosphere in general occurs at scales bigger than 10 meters. So using these models that actually resolve all the sort of flow above 10 meters is actually very useful. The second thing is that even in spite of the fact that there is a lot of turbulence in those small boxes, still that you need to parameterize, that you need to represent in some sense, that problem is simpler than the one of representing the turbulence that exists in a box of 100 by 100 kilometers. And this is just an example of some of the flows that we've been simulating. And the reason I show this is because I want to show the next slide. So one of the issues about this covariance is that people have done this problem in a very modular way. And if you look at the code of a climate model or a weather prediction model, a variety of different problems that are related to turbulence and convection are tackled in different subroutines. So you have a subroutine that does deep convection. You have another one that does moist convection in the boundary layer, another one that does dry convective boundary layers, and so on. Don't worry about the names too much. And one of the things that people have tried to do in the last 10 to 12 years is really to bring those things together. And if you actually break a grid box before you do your Reynolds averaging and decomposition, you actually divide your grid box in areas that have sort of ascending motion and areas that have descending motion. And so you break it into sort of an updraft, downdraft decomposition, or you can call it plumes. you actually end up with an expression for that covariance that is a little bit more complex or sophisticated than the previous one, because you have three terms now there. You have the amount of turbulence that exists inside these updraft regions. So AU is the area of the box that is occupied by these very strong plumes. Then you have another term that is about the turbulence that exists, so the mixing that exists in the areas around those plumes. And then a fundamental third term, which is about the interaction between those plumes that penetrate the environment and the environment around them. And if you do a bunch of simplifications and don't worry too much about the details, you end up with an expression that allows you to represent that covariance by two terms. One is a diffusivity term that tries to represent a more sort of Gaussian-like mixing type. And another one that is what people call the mass flux term here, which is really trying to represent some of the bulk properties of those ensembles of plumes, which is the area that the plumes occupy, how energetic they are, and what the properties are. And then the difference between the plume properties and the mean actually give you the interaction between the two. And so if you look at the previous LES plots and you cut a slice through the clouds, and you plot all the little points that are there, and you're talking about maybe 1 million points, you can plot again something like you have the water vapor here. Here you have the vertical velocity, so all these points are going up, and all the points to the left of zero are coming down. And over here it's zero because it's the water vapor minus the mean, so don't worry about that. But all these points have more water than these points over here. And you notice that there's two sort of, if you look at this type of simple histogram, there's two sort of fundamental regimes. There's a black regime that is more sort of Gaussian-like, that is sort of taken care by this diffusivity part. But there's another skewed part of the distribution that really represents the properties of the plumes, and that's where you try to have to make an effort to come up with good models for these plumes. Now, I could easily spend the next 5 or 10 minutes explaining you the models of the plumes. We don't have the time because I want to highlight a couple of other things. So we talk about these very high resolution models, and they're very useful. And of course, we do a bunch of them, different situations, and Navier-Stokes are the same everywhere you go. So in reality, by doing a bunch of them, you're really doing a lot of it. But they still have a limitation. You can't cover the globe with these very high resolution models, otherwise you would do it, right? And there is a resource that we haven't explored yet, and we're trying to explore, which is satellite data. There's a lot of information from space that, of course, not having the resolution that the high-resolution models do have, and we will never have it from space, not in the same way, but they do give you a global coverage. They do go over a variety of regimes and give you sort of a perception of the complexity of the problem. This is just one example, and I don't want to bother you with too many examples. This is just a plot. This is just liquid water path. So liquid water path is basically the integrated value of liquid water at every level inside the cloud. So it's how much water is there in that cloud. And what we do here, we grabbed a bunch of data with resolutions about 1 kilometer. Now, the LES models have resolutions of 10 meters, but the GCMs have resolutions of 100 kilometers. So even 1 kilometer can be extremely useful, although not being of the sort of detail of the LES. And you can see, so we have about 100,000 snapshots of 200 by 200 kilometers square, which basically is a GCM grid box. And you can see this sort of different types of cloud regimes. So what you see here is, again, this liquid water path. The white part is when you have a lot of clouds. The dark is when you don't have clouds. And we actually, in this particular paper, we're studying a transition from stratified clouds, like stratus clouds that you see off the coast of California, typically in summer. And this is more the type of clouds that you see close to Hawaii. And there's a variety of structure here that you really need to try to represent. But even the simpler things like plotting the PDFs and being able to come up with equations that describe the PDFs is something that we haven't been able to do very well yet. And in this case, you can see the striking example, the striking difference between a Gaussian PDF of this liquid water path in this sort of nicely well-behaved regimes and a very skewed distribution when you have regimes dominated by these very skewed plumes that sort of penetrate the environment and cause a lot of turmoil. Now, this actually highlights the fact that there's a lot of high-resolution data from satellite that we could explore much better. One last example of things that you can do from satellite, and again, I wanted to just give you a very sort of summarized flavor of the things that we can do, is a plot that we get from the atmospheric infrared sounder instrument. So AIRS is an instrument that looks at the atmosphere in the infrared at many, many, many different channels. And because of that, can actually estimate the temperature at many different levels. And with a resolution in the horizontal of about 10 kilometers. And although not perfect, it's really a very powerful instrument in many respects. But it can tell you things that can help you not only to develop better representations of turbulence and convection, but also evaluate your models after you do that and you implement them. And this is an example of the things you can do. So this is about the standard deviation of temperature and the scaling as function of length scale. And this is 100 kilometers, this is 1,000, that's 10,000. And the different colors, and I apologize for the quality of the figure again, the different colors represent different levels in the atmosphere. So this is close to the surface, this is about 1.5 kilometers above, this is 3 kilometers above the surface. And you can see that there is not only a scaling that follows what you would expect theoretically in many respects, a scaling to the k to the minus 3 in the larger scales, and a scaling of k to the minus 5/3 in the smaller scales, you have this sort of scale break at about 400 to 500 kilometers. Now, this study, which is much deeper than just this plot, actually highlights the fact that, for example, water and temperature scale in different ways, and that there is a variety of scaling behaviors that, the theory that we have right now and even the models that we have cannot really explain very well. So this is a great data set, not only to improve the climate models, but to really understand the overall turbulence and convective structure of the atmosphere. So I have my yellow light. I'll finish with a summary, summary of a summary. So one of the things I really tried to highlight is the fact that unless we understand and represent turbulence and convection better, and the small-scale mixing, we will never have climate prediction that we really can rely upon as much as we would like to. And I'm careful about what I'm saying so that it's not misinterpreted. The LES models, these large Eddy simulation models, have resolutions of about 10 by 10 by 10 meters, are unbelievable tools to try to really understand what's going on and to help us come up with these dynamic equations for the statistical properties and bring this into the models and try to improve them. I highlighted the fact that we're trying to bring together concepts like diffusivity and plumes that come from sort of different areas of research in a way, but have been brought together as much as possible to represent these two sort of scales. So there's this large resolved scale that we do with our numerical resolved advection. But then in the subgrid, we have these two scales, a much smaller scale, much more Gaussian one, then another one that is sort of skewed and really plays a key role in mixing the properties in the atmosphere. And finally, just a little flavor of the fact that there is a huge amount of high-resolution satellite data that is vastly unexplored, and it's available to anyone to actually look at that and try to understand better what happens in the atmosphere and come up with better ideas of how to represent turbulence and convection in our climate models. So, thank you.
So, any question?
Oh, so this is a real short summary. Eddy diffusivity is an idea that has been around for 150 years. And not in climate models, obviously, but from Reynolds and Buzinesk and Sanvana and a variety of other scientists. What we do in terms of eddy diffusivity in climate models, in many respects, follows a lot of the turbulence work that has been going on since the 1920s and 1930s. It doesn't fundamentally diverge from that. So anything that you go back to the 1920s and after that, that's what you follow. Now, there's a variety of different details. I'm happy to talk to you in detail about that. I didn't try to, I couldn't spend 12 minutes, even if I wanted, to explain all the different flavors of it.
So, thank you. So we now have the last talk of the session by Hide Yamazaki.
Thank you for giving me opportunity to spend last talk on phytoplankton. Now I'm discussing, how phytoplankton distribute in space. Which one is this? Okay, biologists use, bottle to sample phytoplankton. Usually, bottle is around meter scale, so phytoplankton you have no idea how phytoplankton distribute less than 1 meter scale. Conventional CDD may carry fluorescence like this might give you some idea how it distributes less than 1 meter scale, but usually CTD is on tether, so it's got, sort of strip motion, difficult to interpret, this sort of signal. This is my microstructure profiler that measures turbulence as well as centimeter scale fluorescence field with this LED probe. I wanted to know difference between centimeter scale and millimeter scale. So I developed another fluorescence probe based on laser that can resolve millimeter scale in space. And also I developed next generation of my microstructure profiler that carry both LED and laser. So I have centimeter scale and millimeter scale fluorescence signal from, too close? Sorry. Okay. So from same statistical field, I have 2 centimeter scale and millimeter scale data. Okay, let's compare these data set. This is CTD fluorescence signal, and this is LED centimeter scale signal. Both shows some intermittency, but LED has more intermittent feature than CTD. This is millimeter scale fluorescence data that has lots more, intermittent feature. Are we looking at the same data? So we start, averaging from 2 centimeter, 10 centimeter, 50 to 1 meter. What 1 meter scale, both agree. So if you average over, you lose all these intermittent nature. Okay, I'm going to show you one more example with laser, LED, and CTD, as well as, this bottle sample. Okay, we computed the mean from all these 3 fluorescence data. Niskin give me only mean, and also meter scale variance. Plotted against mean versus standard deviation. This is basically variation covariance. CTD has no variance, so there's no standard deviation. Niskin bottle. CTD has some standard deviation, but not as large as LED. Laser gave me very strong standard deviation. Because of this feature, we collected all kind of data set from various places, like this place, this lake, and Seto Inlet, and also from coastal area, and river mouths, and also estuaries, as well as Kuroshio extension, and we came all the way to Santa Barbara Channel as well. And we plotted mean against standard deviation from all these data sets. We came up with some feature, but we still haven't come up with general tendency. However, all these low standard deviation part is coming from river mouth or estuary, which has freshwater influence. This is from open water, such as Kuroshio extension. In general, Kuroshio is oligotrophic. People think it's a desert, but look at this. Mean is small, but standard deviation is large. Okay, I'm going to look at signal differently from statistical sense. This is LES and laser. Let's look at the spectrum of these 2 time series. Time series shows up to 1 meter scale over is conventional turbulence minus 5/3. But LES, this part shows some colorness. However, green laser shows white feature. I was a bit scratching head because these 2 time series supposed to came from same statistical field. The only reason this can become white is time series no longer conventional Gaussian stochastic process. It's a point process. So we looked at, signal itself. LED and laser, and this is just a histogram, both shows very skewed distribution. If signal behave like turbulence signal, they may follow log normal distribution. Indeed, LED follow log normal distribution, but laser is not. So we took another log to the signal, which become, Gaussian. This is Gamble distribution, which is, extreme value distribution. So at 2 centimeter and millimeter scale, they are completely different signal. So discreteness happens at millimeter scale, and signals are now in point process. How does micropatch distribution distribute in space? So we looked at the peak based on some threshold. For this one, we use twice as much of mean value as a threshold. If these events happen in complete random sense, then the process has to be Poisson. Indeed, this threshold gave me Poisson process. But if you lower the threshold to count with smaller feature, it's not Poisson. It's more skewed toward big clump. So, counting smaller aggregate, they are more like clump to big aggregate. It's not random. Next, what I wanted to do was, I wanted to see what we are dealing with. So I mounted camera system using LED as a light source. So whatever signal getting into LED probe, I may be able to see what they are. This is again LED and laser probe. Okay, now these peak, we see feature what they are. Then you go through image analysis, detect edges and so forth, and scale, measure the size, major axis and minor axis and so forth, and then you count how many of them you came across. Now I'm getting size spectrum like this. There is certainly two scale law. There is a kink here. We are not sure how this kink is general, but this kink is close to Kolmogorov scale, so we might be seeing difference between inertia and viscous regime. Okay, next we compile all those large data set, then compute mean particle size against turbulence intensity. My probe profiler carries shear probe, so I can directly measure turbulence intensity. As you see, turbulence increase, intensity increase, particle size increase, up to more or less Kolmogorov scale. This has been hypothesized or developed few theory, but this is the first data set that shows reality has this tendency as well. Next one is we looked at nearest neighbor distance against number of particles we came across in the data set. As you expect, because you have more points, nearest neighbor distance decrease. However, nearest neighbor distance is independent of turbulence intensity. We looked at those features and measured the size of small aggregate, but we couldn't tell what they are. So I invited my colleague from England to use holographic system, because this system can resolve 15 micrometer scale that may give us, clue what we are dealing with. As a matter of fact, when he looked at this is a fluorescence, profile from his holographic system. This is a raw holographic system. Go through image post-processing. He came up with this image. This is roughly millimeter scale small aggregate, and from my laser probe is indicating this is not dead particle. It's bunch of stuff is in, and fluorescence is coming from this. So I think what we are coming across picture is, image Azam created in 1986. There's a hotspot in space. A bunch of action is taking place around this hotspot. And this is, Roman Stoker's group recently, came up with image, how microscale, ecosystem look like. Indeed, what we are getting is, image like that as a real, image. Then what would you do about ecosystem model? I think that's the link to this, session. Okay, we want to develop NPZ eventually, but we started from NP, nutrient and phytoplankton ecosystem model. What we're doing is because P, when we looked at small scale P, it's got the mean and the standard deviation. So as usual for the turbulence lecture, why not decompose into mean and fluctuating component and go through similar Reynolds decomposition and came up with variance equation. Take example these transfer function. You can come up with 5 equation. You can solve this. However, story or life is not that simple. Based on initial condition, the solid line is full equation, and dotted line is Reynolds decomposed mean equation. Reynolds decomposed mean equation rapidly approach to converge to full equation, and fluctuation converge to 0 for certain initial condition. Other initial condition did not converge, and worst condition actually diverge. So this is apparently new mathematical instability problem, and we are working on triple correlation term to get rid of this sort of instability. We are not sure how successful next stage is. Anyway, I gonna give you take-home message from my talk. One, discreteness appears at the millimeter scale. So centimeter resolution is not sufficient to study microscale ecosystem. You have to resolve millimeter scale. Difference between centimeter and millimeter scale is so huge. Two, the distribution of micropatch is not completely random. So there is some structure within microscale ecosystem. I don't know what kind of structure and what the role of that structure is. Three, mean patch size increase as the intensity of turbulence increase. This has been, hypothesized, but nobody showed direct, data set. We are the first one to show this is true, indeed. Last three, as I showed, the beginning of our new challenge, NPZ closure has to be developed. That concludes my talk. Thank you.
So, any question?
phytoplankton. Well, some data shows, bigger than Komolov scale. So see, turbulence is intermittent. So depend on the point you sample, you may not getting, right Komolov scale. And because, these guys are so lively, gummy, so they may be able to grow bigger than Komolov scale.
Okay, thank you. I think if we want to take a pause, we should stop here because there will be the Lawrence lecture session in 10 minutes. So thank you for all the speakers for this session, and don't forget the post session tomorrow. Thank you.